All right, this is part 2 of the term 3 review. We're asked to find vertical and horizontal asymptotes for these functions. Now, a vertical asymptote is when the denominator equals 0. Anywhere that a denominator would equal 0. So for this one, we'll have a vertical asymptote at x equal 5/4 and at x equal 1/3. Those are the values that if I put them in would make these 0. Now you want to check and see if any of these had canceled. That wouldn't be a vertical asymptote anymore. That would actually be a hole in the graph, what we call a removable discontinuity. These are non-removable. These aren't going anywhere. Okay. So the same thing over here. My vertical asymptote for this would be at x equals 0, because if I put 0 in, I get 0 in the denominator. Now this one, actually, if I put 0 in here, I get 0 over 0. So actually, I need to be a little careful here. All right. If I were to take the limit of this as x approaches 0, all right, I get 0 over 0. So then if I use L'Hopital's rule, take the derivative of the top, derivative of the bottom, try it again, I actually end up with 1 over 1, which is 1. So in a strange way, what happens here is this graph comes up and it approaches a value of 1 and then goes back down, right? And so it's got a little hole in the graph there, but that's not an asymptote. Initially, I thought that was, but the more I thought about it, the more I realized that's just not what's happening there, okay? So that's a vertical asymptote. Now, as far as a horizontal asymptote goes, this is what happens when we take the limit as x goes to infinity. If we let x get bigger and bigger and bigger, does this graph tend to settle on some value, or does it keep getting bigger or smaller? What's going on? So up top, I have 2x times x. That's 2x squared and a bunch of other junk I don't care about. On the bottom, 4x times -3. That's a -12x squared and a bunch of junk I don't know. See how the x squareds are the same magnitude? So when I let x get bigger and bigger, these are going to get bigger and bigger at kind of a similar rate. And over time, all this other stuff will melt away. And what will happen is these will start to gravitate to the ratio of the numbers in front of them. In other words, we're going to have a horizontal asymptote at y equal -1/6. That's what this reduces to. Okay, that'll be our horizontal asymptote for that. Similar idea here. If I let x get bigger and bigger, sine's just going to keep going from 1 and -1. It's not really going to move past that. But this bottom is going to keep getting bigger and bigger and bigger and bigger. And so these terms will get smaller and smaller and smaller and smaller. And so we do have a horizontal asymptote at y equals 0. Because again, the denominator will keep getting bigger and bigger, but the top will just keep going between 1 and -1. And so this graph will continue. In fact, what this graph really looks like is, it goes like that, but then it comes here and it gets like closer and closer and closer to 0 on both sides. All right, number 6, write a differential equation that represents the situation. The rate of change of the deer population, so let's try that first. Rate of change of the population, dp dt, okay, is proportional, so we'll put that k in there, to the carrying capacity of the environment, L. So it's proportional to the actual capacity, L, and the difference between the carrying capacity and the population, and the difference between carrying capacity and population. Just like that right there. All right? So that's just using that as our guide there. Now this one asks us to draw a slope field for this, and these aren't bad. You just have to, kind of stay with it. So at 0, 0, we're going to have this. At 0, 1, it'll be -1. At 0, 2, it'll be -2. At -1, 0, or I'm sorry, at -1, 0, it'll be +1. At -2, 0, it'll be +2. Okay, go up to 1 here. 0, 1 will have a slope of 1. All right, 1, 1 will have a slope of 0. 2, 1 will have a slope of -1. -1, 1 will be a slope of 2, and this will be a slope of 3. Okay, if I go up, 0, 2 will have a slope of 2. 1, 2 will have a slope of 1. 2, 2 has a slope of 0. And then -1, 2 will have a slope of 3, and then a slope of 4. Okay. Come down, 0, -1 will have a slope of 1. Okay, 1, -1 will have a slope of 2, slope of 3. This will have a slope of 0. This will have a slope of -1. And then finally, at -2 will have a slope of 0, then of 1, 2, 3, and 4. All right, so this is what we end up with. 0 is going this way, positive slopes here, except for there. I'm sorry, negative slopes right in there. Okay, a couple spots there. And then that. All right, so this is what we end up with. I'm looking down here. I'm starting to doubt myself here. Let's see, negative. Yeah, I think I screwed these up here. Wasn't quite looking right. Okay, I think these were the right number. I just had them positive instead of negative. So my fault. Sorry if that screwed you up. Okay, so you can see all these are negative down here, positives right there. Okay, that should be a positive as well. I promise I know how to do these. All right, so positives on this side, negatives on that side. All right, so then it says shade the portion of the graph where y is concave up. Now, in order to know that, we're going to take the second derivative. And the second derivative of this will be dy dx minus 1. Well, dy dx is y minus x. So I'm going to take that y minus x, I'm going to put that in for dy dx. And here's our second derivative. All right? And if we're concave up, that's when our second derivative is positive. So this is when y is greater than x plus 1. So if I come back here, I go to positive 1, up 1 over 1, kind of draw this line in here. Okay, that's the line x plus 1, and we want to be greater than it. So that'd put us in this part right here. Let's just use some old school algebra on that. All right, find the equation of tangent line here to this equation. So what I want to do is take the derivative. Derivative of this could be 6x plus 2y times dy dx. Derivative 1 is 0 equals, treat this as a product here. Derivative of 5x is 5 times y as is plus 5x times the derivative of y, which is dy dx. Okay, so this is what we get. I would go ahead and put 1 and 4 in right now. So if you do that here, you're going to get 6 plus 8 dy dx equals 20 plus 5 dy dx. Okay, if I subtract that, I'm going to get 3 dy dx, 8 of them minus 5 of them, equals 20 minus 6, that's 14. Divide, we get dy dx equal to 14 thirds. Okay, so there's our slope. We had our point. So y minus y equals slope times x minus x. And then number 10 here, they give us a table, and they say f and g are inverses, so what would these be, right? So g of 2. So if I do f, g, like this, what they're saying is when x is 2 for g, what does the value equal? Well, when x is 2 for g, that means f equals 2 there, right? So when did f equal 2? Right here, when its x value was 1. So when x is 1, f is 2. That means when x is 2 for g, its value would be 1. So 1 is our answer here. Okay. Now b says, well, what's the derivative at that point? So if we explore a little bit further, we see at that point for f, it had a slope of 3. So our slope then would be 1/3. For these other two, it's the same idea, we just have to change the x value. So now we're saying when x is 1 for g, what's going on? So that's when f equals 1. Well, f equaled 1 right here when its x value was 2, and it had a slope of 0. Okay, so that means at the point 1, 2 for g, it has a slope that is undefined. Same idea here. If I go f, g, all right, and say x is 3 for g, when did f equal 3? Well, f equaled 3 right there, when its x value was 0. And what was the slope at that spot? Slope was 2, so our slope would be 1/2. And there's part 2.